All right. So I'd like to start with some definitions. Okay, you guys have seen these words before. You've seen the word polynomial, but I know that sometimes it's hard to remember, especially if it's been a while. So I just want to review that. Our first outcome in this course is going to look at polynomial functions. So we should know what they mean. Do you guys know what a polynomial is? Or perhaps you can give me an example of a polynomial. Have you heard the word before? Oh, yes.
Well, I don't know the exact one from math, but it was like multiple of like a group of terms.
Yeah, so poly means many terms. Yeah, so that's great. We're getting there. What specifically are like the types of terms? Like I have a chart here. I'd like to put some examples and non-examples because when you compare what is a polynomial with what isn't a polynomial, sometimes that makes the definition really clear. Okay? So do you guys have any examples of a polynomial function? Yeah.
2x squared plus 3x minus 4.
Yeah, so that is a polynomial. Polynomial function just means we use a second variable, right? So you said 2x squared plus 3x minus 1, or something like that? Yeah, so if it's a polynomial function, it would just be y equals 2x squared plus 3x minus 1. Okay? That would be an example of a polynomial function. A polynomial, just a polynomial, would be the 2x squared plus 3x minus 1. That's called a polynomial expression. Okay? Any other examples of polynomials? Okay, you guys have phones? Take out your phones, go to Google, and Google examples of polynomials. And tell me what you come up with. Okay, yeah, y equals 4 is a polynomial function. Okay, any other examples? You could just Google examples of polynomials. Yeah?
Y equals 2x minus 5.
Yes, y equals 2x minus 5. Okay, anything else? Yep.
Y equals x minus 3.
Yes. Okay, I'm going to put some bigger ones on there too. Let's say I have y equals 5x cubed plus 2x minus 4. Y equals x to the 11 plus 3x to the 7. That's also a polynomial function. Okay. All right, now let's talk about what isn't a polynomial function. So maybe Google non-polynomial functions. Yes, or you have one?
A negative exponent
Mm-hmm.
or anything
Yes, so y equals negative, or x to the negative 1 rather, right? So back in grade 10, you would have learned that we can interpret this as if this is a denominator of 1 over x to the 1, or just 1 over x. Okay, because we bring a negative exponent, if it's in the numerator, down to the denominator, then it becomes positive. Okay, you're correct. This is not a polynomial function. So we cannot have a variable in the denominator position. Okay, you also spoke about fractional exponents. Yes, so something like this, x to the 1/2. Okay, and then again, in grade 10, do you guys remember what an equivalent form of x to the 1/2 is? Yeah?
I think wouldn't it be like x squared rooted?
Exactly. Fractional exponents are essentially radicals. So in this case, we're looking at the square root of x because the denominator of the exponent becomes the index of the radical. Okay, so yes, you're right. Radicals are not polynomial functions. They are functions, they're just a different type of function. Yes? Yeah, so a decimal in the exponent is the same thing. So you could write this as x to the 0.5. Same idea, right? Anything else? There's one other that I can think of, or a couple others actually that we're even going to look at in this course. Something like this, okay, where the variable is actually in the exponent position. That is not a polynomial function. That's called actually an exponential function. Okay? This first one, by the way, is called a rational function or reciprocal function. Okay, rational meaning like rational numbers, like a fraction. And this one over here is called a radical function. Okay? Those are all different families of functions. And in fact, this one, y equals 2 to the x, we're going to look at in this course. Another one that we'll look at in this course is y equals sine x. This is a trigonometric function. Okay? These are functions, but they are not polynomial functions. Okay? So a polynomial function, I think what I'd like to do first is just actually define a polynomial. A function is just when you set that equal to another variable. Okay? A polynomial is essentially a sum of various powers of x. Okay, and actually, I'm going to break that down even a little more. Sorry. Various powers of x. Let's write that it's the sum of numbers and variables. Let's do it that way. And in fact, numbers and variables that can be multiplied by numbers as well. So for example, this 2x squared here is 2 times x times x. Okay, that's 2 times a number, or times a variable, plus there we're adding 3 times x, and then minus 1. Okay, now over here, you know what? Sorry, I don't like this definition. We're adding terms, right? But it's the sum of various terms consisting of, that's better, products of numbers and variables. Okay. So we're adding lots of terms together. Each term is a product, a multiplication of numbers and variables. Like, for example, this one is 2 times x times x. So we're multiplying numbers and variables. Then we're adding another term. This one is 3 times x. Then we're adding a negative 1. I like that better. Okay, this is not that. Y equals 2 to the power x is not a product of a number and a variable. We're taking a number and we're raising it to a variable exponent. That's different. Okay. Degree. Okay, degree of a polynomial. So let's just see if you guys remember this. Let's look at this first example, y equals 2x squared plus 3x minus 1. Does anyone know what the degree of that polynomial is? Yeah, it's 2, exactly. What about this guy, y equals 4? This one is actually 0. Yeah, because there's no x term there. This next one, though, is 1. Yeah. What about this guy? What would the degree be here?
It would be 77.
Not quite. Sorry?
Do you add or multiply the exponent?
Okay, so let's get into that. So the degree of a term is the sum of all of the exponents on that term. Okay? If there's only one variable, then the degree is whatever the exponent is on that variable. And that's what we saw so far. If you have something like a squared b cubed, then you would add the 2 and the 3 together to get 5. Okay? And actually, let's look at that. So for example, okay, the degree here is 5. The reason for that is degree is actually the number of variables that you're multiplying together. And so if you think about this being expanded, okay, that's a string of 5 variables. And so that's why we add the exponents. The degree there would be 5. Okay? Usually, in the context of polynomial functions, we're only going to be working with, we're working with 2 variables, but y is isolated. So we're really just looking at the degree on the x side. And so if you have a term like this, okay, that's going to be a string of 7 x's. So there's 7 x's being multiplied together. Degree is 7. Okay? When you have the number 4, there's no x's being multiplied together there. So that's why the degree is 0. Okay? The degree of a polynomial, because we just talked about degree of a term, and there's often many terms in a polynomial. Degree of a polynomial is the highest degree amongst all the terms. Okay, so for example, if I had this guy, x to the 11 plus 3x to the 7. Okay, 2 terms. This one has degree 11. This one has degree 7. So overall, the degree is 11, because you go with the highest. Okay? Leading coefficient. So firstly, what's a coefficient? What's the coefficient of... What are the coefficients in this first polynomial, 2x squared plus 3x minus 1? 2 and 3. Yeah. So a coefficient is a number in front of a variable. Okay? So here I would say the coefficient of x squared is 2. And the coefficient of x is 3. Is 1 a coefficient? No, it has another name, though. Do you guys remember what those are called? Starts with a C as well. Constant. Yes, exactly. Okay? So, leading coefficient. The leading coefficient of a polynomial is the coefficient of the term with the highest degree. Okay, let's look at this example here. X to the 11 plus 3x to the 7. Okay, what is the term with the highest degree in that polynomial? In this example right here. X to the 11. What's the number that's in front of that? A 1, exactly. So here the leading coefficient is 1. Okay, so whoops. X to the 11 plus 3x to the 7. Leading coefficient is 1 because there's an imaginary 1 in front of the x to be like. Okay? What if I had something like this? Whoops. 5 minus 2x. What's the leading coefficient there? Yes. Almost. It's not 5. So leading, by the way, is not always the first. So let's look at each term. What is the degree of the number 5? 0. What's the degree of this guy? 1. So this is the leading term. Okay. What's the coefficient of that? -2. Yes. So coefficients have signs. Okay? All right. End behavior. So the end behavior of a function is a description of what happens to the function as you move from left to right on the x-axis. Okay? Okay. Now, there are actually a lot of different ways.
Casey Austin, please come to guidance. Casey Austin, please come to guidance.
There are a lot of different ways that we can describe this. You can describe it using words, but typically the way that's sort of accepted and not ambiguous is to use the 4 quadrants of the coordinate plane. So this is the first quadrant, and then you move around counterclockwise. This is quadrant 2, quadrant 3, quadrant 4. Okay? So let's say we have a graph that looks like this. Okay? The end behavior would be like what's happening with the 2 arrows. As you move from left to right, the graph starts in quadrant 2 and ends in quadrant 1. So the end behavior here would just be Q2 to Q1. Okay? If you have something like this, let's do one more example. Okay? Where does this guy start from left to right? Quadrant 4, and where does it end on the right? 1, yeah. So this is Q4 to Q1. Okay? A turning point. And by the way, another thing that we can say about most functions that end in quadrant 1 is that they're increasing. Because as you go up this way, you're going to be increasing. Okay? The only ones that aren't like that are horizontal lines. Right? A horizontal line could end in quadrant 1, but it's neither increasing nor decreasing. Okay? And then similarly, if a function ends in quadrant 3, we would say it's decreasing. Right? The 2 quadrants on the right side of the coordinate plane are, sorry, not 1 and 3, 1 and 4. So it'll either end in quadrant 1 or quadrant 4. Most of them, actually. You may have something that goes like that, I suppose. But for this course, for the purpose of this course, you're going to have something that ends in quadrant 1 or quadrant 4. Oftentimes, if it ends in quadrant 1, it's increasing. If it ends in quadrant 4, it's decreasing. Okay? But actually, there are exceptions to that. Which is why it's really crystal clear if you just use the quadrant thing rather than start to play around with like writing an essay about what this thing looks like. Okay? A turning point on a graph is the point where a function changes from increasing to decreasing or decreasing to increasing. And that's actually going to create a maximum or minimum point, or a local maximum or minimum point, okay? So it's the point where the function turns from increasing to decreasing or vice versa. So if we look at this example, there are 3 turning points here. There's one here, and one here, right? Those are the turn points. Here it starts decreasing, and then here it turns and starts to increase. Then it starts to decrease again over here, and then here it starts to increase. Okay? All right. So here's what you're expected to do in this course for this outcome. You're expected to be able to analyze and graph polynomial functions and include discussion around intercepts, turning points, max mins, domain and range, and you can do this using technology. Okay? We don't, to be honest, in this course, expect you to graph much, if anything, by hand, which is kind of nice. And one thing that you'll notice about this course is that it's very, very application-based. So whereas in like a 30-1 or a 20-1, we look at the algebra, where we might look at, for example, transformations. What happens if you translate something or stretch it or compress it or whatever. In this course, we're more interested in what can we use this type of function to model? And then how can we answer questions about that particular situation using a function? Okay, so there's not quite as much algebra, but there's a lot more application. There's almost always a function is connected to a particular context. Okay. So in this course, the other thing is that we only look at polynomial functions up to degree 3. So we are going to look at degree 1, degree 2, and degree 3. And we're going to kind of do them one day at a time. Okay? All right. So the first thing we're going to look at is a polynomial function of degree 1. Okay? Now, do you guys know what these are called? You would have seen them in grade 10. Somebody said that. I heard something. What? Linear. Yeah. They are also called linear. Whoops, let's make that black. Linear functions. And they are called linear functions because they form a line when graphed. Okay? Standard form of a linear function is f of x equals ax plus b. I know in grade 10 we talked about y equals mx plus b, or f of x equals mx plus b. Do you guys remember that? Yeah? And what did m represent? The slope. Yes. So in this format, f of x equals ax plus b. A is just the slope value. You could use an m here. The reason why I'm going to use the letter A instead is because what we're going to try and do in this outcome is make some generalizations about polynomial functions as a whole, depending on the leading coefficient. And so I'm going to just use the letter A for every polynomial function that we look at. It could be linear, could be a degree 2, which is called quadratic, or it could be degree 3, which is cubic. And I'm just going to use that same letter A for all 3 of them for the leading coefficient, because we're kind of moving away from slope, it is the slope, and moving towards what can we say about the leading coefficient of all polynomial functions and how that's going to affect the graph. Okay? So let's sketch these graphs, and we'll put them on this grid. Now, you can always use technology to do this. But I do just kind of want to review how you could graph these by hand as well, just because I know that a lot of you are planning to take more math after this. And so I like to kind of model what that would look like, just review what you've seen before. And this is not new. It just may have been a little while ago. Okay? So these are both linear functions. F of x equals 2x minus 3, and g of x equals negative 3 plus 1. Right? It's written in function notation. You can kind of replace the f of x and the g of x with y. But essentially, when you have something in this form, ax plus b or mx plus b, the m value, in this case it's 2, represents the slope. And what does the b value represent? Y-intercept, yes. So if we're starting with f of x, then I'm going to start by plotting my y-intercept. In this case, it's at negative 3, which is right there. And then how could I find another point on the line? Yeah. What do we need? What's that? Yeah. Yeah. Right. So slope is rise over run. And remember, the rise and the run, depending on the sign, indicate a direction. These are both positive. That means we're going to go up and right. So we're going to go up 2, right 1. Up 2, right 1. Okay? So here is the one line f of x. And then I'm going to do this one in a different color. So g of x, our starting point, the b value is 1. So I'm going to start there. And then this is negative 3 over 1. So negative 3, if our rise is negative 3, that means we go down 3 and then right 1. Okay, so I'm going to go down 1, 2, 3, right 1, down 1, 2, 3, right 1. You could also think of this as 3 over negative 1, because it's the same as negative 3 over 1, has the same value. In that case, if it's 3 over negative 1, you would go up first. And then negative 1 means you're going left. But either way, these points are all on the same line. Okay, that wasn't a very good. There we go. You guys get the idea. So this is g of x. Okay, so we've got these two functions. I would like to just talk a little bit about some properties of each one, and then let's try and make some generalizations. Okay, so in the first guy, f of x, what is the constant in this function? Yeah, right. Okay, what is the sign of the leading coefficient? Let's start with what is the leading coefficient? 2. Okay, what's the sign of 2? Positive. Yep. End behavior. Where does f of x start and where does it end? From left to right. Yep. Yeah, so it starts down here, which is in quadrant 3. Remember, this is always quadrant 1 and then 2, 3, 4. So end behavior is quadrant 3 to quadrant 1. Oh, wait, I'll use Roman numerals. If you don't use Roman numerals, I don't really care. But you should know what they are, because you may be given a description of end behavior with the Roman numerals, and you need to be able to recognize that. What is the domain of f of x? What is the domain? Yes? Yeah, x can be anything, right? Those two arrows, horizontally, this one over here is pointing left, and this one's pointing right. So that means x can be anything. Okay, so x is an element of the real numbers. What about the range? Same thing, yeah. y is an element of the real numbers. Okay? All right, let's move to g of x. Okay, constant term for g of x. 1, yes. What's the sign of the leading coefficient? Negative, that's right. Okay. The end behavior, where does it start? Where does it end? Yeah, so it goes from quadrant 2 to quadrant 4. Okay. What is the domain? And what's the range? Yeah, they're both elements of the reals. So x is an element of the real numbers, and y is an element of the real numbers. Okay? So in general, we're going to make some generalizations here. What can we say about all linear functions? Well, firstly, let's talk about this constant term. Where does the constant term appear on the graph? Yeah.
On the y-axis.
Exactly. So the constant is the y-intercept. Okay, sign of the leading coefficient. So if that a value is positive, what do you think that's going to affect? What factor do you think that's going to affect if a is positive? Yeah. It is going to affect the slope, you're right, right? But in terms of what we outlined here, what do you think it's going to affect if a is positive? Yeah.
What
Yeah, it affects the end behavior, right? And because we're talking about slope here, a is slope, you're right, right? If slope is positive, the graph is going to end going up. And if slope is negative, the graph's going to end going down, right? But in general, that would be the end behavior, okay? So the coefficient, the leading coefficient, the sign affects the end behavior. Okay, so if a is positive, if a is greater than 0, okay, then we get this situation going on. It will always start in quadrant 3 and end in quadrant 1 because it's going to slope upwards. Okay, if a is negative, less than 0, it's going to start in quadrant 2 and then in quadrant 4. Okay, what can we say about domain and range of linear functions? Yeah. Yes, so domain and range, x is an element of the real numbers and y is also an element of the real numbers. There's the only exception, and actually it's not the only exception, this comes up a lot, is when you have a context. And in that context, certain values don't make sense. So for example, you might have a linear function that describes, let's say, the cost of X number of shirts, right? So if shirts are $10 each, you buy 0 of them, it costs you $0. You buy 1 of them, it costs you $10. Buy 2, it costs you 20, etc. Right? In that context, that is linear because it's going to make a line when you graph it. But in that context, it does not make sense to have values outside of quadrant 1 because you can't have negative shirts and you can't have negative cost. So in contexts, we will restrict the domain and range accordingly so that the values that we input into the function make sense in that context. Okay? But if a function is not attached to a context, then yes, for a linear function, domain and range are that x and y can be anything. Okay? All right. Let's keep going. All right, so what I like to do in your notes is just kind of tell you this is what's expected of you, and something will either be an acceptable standard or a standard of excellence, okay? Now, this is just taken right out of the curriculum document called the Program of Study, and just so that for your reference, on like a diploma exam, the rule of thumb is that 80% of questions are acceptable standard, 20% are considered standard of excellence. And if you get 80% or above on a diploma, and again, diplomas have not sort of happened in the past couple of years, but if you do, then that you are put into a category called standard of excellence. Okay, so that's what these words mean. So acceptable standard, that cut off from the previous page, student can solve a contextual problem that can be modeled by a polynomial function where the function, table of values, or graph is given. So I'm going to give you a polynomial function. It's attached to a context. Can you tell me about what's going on? Okay. Standard of excellence, can you identify the domain and range for that polynomial function in a context? So that's what I spoke about around restricting domain and range for particular contexts. Okay. I got to say, sometimes when I look at the curricular document and they say this is acceptable and this is standard of excellence, sometimes I'm like, wow, some of those acceptable things are really hard and some of the standard of excellence things are really easy. So, you know, it's not always crystal clear and it's a bit subjective, I suppose. But in general, I would say the standard of excellence are a little bit harder and a little bit less frequent. Okay? So a linear function, c of x equals 0.04x plus 0.79 represents an estimate of the average cost of gas, c of x, for years x starting in 1997. Okay? So we're talking about cost of gas is c of x, x is the year. And it's not, x is not the actual year. X is the number of years from 1997. Okay? So for example, if we're talking about the cost of gas in 1998, what would x be? 1, exactly, right? So x is number of years starting from 1997. If we're talking about 2022, what would x be? 25, yeah, exactly. Okay? So firstly, what is the rate of change for this equation? Let's talk about that first. Rate of change. It's a number. Yeah. Yes, okay, so rate of change, the numerical value of rate of change is the slope value, right? So the numerical value is 0.04. In a context, though, we do need to include units in that. And as a general rule of thumb, the units for rate of change are always y per x. Okay? Now, you have to replace y with what is y in this situation. It's cost, it's money, dollars. Per x is years. So in this case, the rate of change is 4 cents per year. Okay, what does that mean? What's happening to the cost of gas? Increasing, yeah. Increases by 4 cents per year, okay? You could also answer it that way. You could say, every year the cost of gas goes up by 4 cents. That's fine too. Okay? What does the c of x intercept represent in context to the question? So firstly, what is the c of x intercept? Well, look at the equation. So c of x is like y, right? So we're looking at like y-intercept in the context. So firstly, what is that y-intercept? Yeah?
Cost of gas per year?
That's Well, cost of gas per year, I'm not sure if that exactly makes sense because in a particular year, the average cost of gas is going to be this. We can talk about how much the cost of gas increases or decreases per year, which is the 0.04. Okay? But let's make this simple. Give me the numerical value of the C of x intercept. Yeah. What's the number? C of x is in the y position of this equation. Think y equals mx plus b. Y-intercept. Where do you see that on the function? Yeah, 0.79. Okay, C of x intercept is 0.79. Okay, now here's where intercepts are incredibly important. Okay, that's on the y-axis. If we're on the y-axis, what coordinate do we always know? Yeah. X is 0. So oftentimes, the C of x intercept, the y-intercept of the linear function, represents the value at the start. Okay? X is 0 on the C of x intercept. C of x is 0.79. What are the units for this axis? The units for C of x. C of x represents what? Cost, so it's dollars. And the units along here? Years. It's actually years since 1997. Okay, so what does that 0.79 mean? Can we put this into a sentence? Yeah.
C of x is the total amount of, or the total cost of
Gas, yeah.
gas for that year.
In what year? 1997, yes. So what does it represent in the context? It's the cost of gas in 1997, okay? This is a big emphasis of this course. Being able to take a function that represents a context and speak to that context. And if I ask you a question like this, and you just answer 0.79, you will get 0. Because I've asked you, what does it represent in the context? Okay? So you have to be really, really crystal clear of specifically what does the y-axis represent? What are its units? What does the x-axis represent? What are its units? And speak to those units. You can even say 0 years after 1997, the cost of gas is 79 cents, right? That would be a good explanation. But in general, particularly if the x variable represents time, this is going to be at the start. Y-intercept is at the start because on the y-axis, time is 0. Okay? All right. Assuming this growth trend continues, what will be the price of gas in the year 2018? My guess is that the last time I changed these notes was 2018. Whoops. It's been a long time. Okay, assuming the growth trend continues, what will the price of gas be in the year 2018? Okay, so year 2018. That is a time, right? Time represents which of the variables? X. So here what's happening, we're given an x value, we want to know the y value. This is a really common thing as well in this course where it's like, okay, here's a function. You got two variables, x and y. If x is this, what's y? Or if y is this, what's x? In this case, we're given an x value. But not exactly, because 2018 is not going to be the x value. What is the x value? 21, right? So 2018 minus 1997 is 21. So this is x. So what we're looking for here is C of 21, which is 0.04 times 21 plus 0.79. And that is, I think, $1.63. Yeah. This is probably not in Alberta, somewhere else. Okay. Domain and range within the context of this question. Okay, so X represents years since 1997. What makes sense? Could I have any number? Yes. Beautiful. Yes. X is greater than or equal to 0 because we're looking into the future, not the past. Okay. What about the range? What's the lowest cost of gas that you could have? Yeah. Exactly. Y is greater than or equal to 0.79. Or I would actually use, instead of y, C of x. Okay? A really, really good question to ask yourself when you're trying to figure out domain and range for a context is, could this value be negative? Sometimes it can. If you're talking like about the temperature outside, you can have negative values there. But oftentimes, that will help you to figure out what's possible. Okay, questions? Oh, I think I have another example here. There we go. Okay. Here we're given a graph. So in the first example, that's another thing I should talk about. You're going to be given multiple representations of these functions and be asked to answer questions about them. Sometimes you're given an equation, like in that last example. Sometimes you're given a graph. Sometimes you are given a table of values. Sometimes you're just given a description. So a description in that last example would be the cost of gas in 1997 was 79 cents per liter. Every year, the cost of gas increases by 4 cents a year. Right? That's a description in words of what's happening. Okay? The graph below represents the time it takes for a tank to drain completely. Okay, so first question, how long does it take the tank to completely empty? How long does it take? Yeah, so it's right here. This is where the tank is empty. Right? Now, why does that make sense? Because the volume is the y-intercept. Sorry, the y-axis rather, right? So if the tank is empty, then we're looking at a volume of 0. Okay? Volume of 0, when the y value is 0, we're looking at the x-intercept. Okay? Now, yeah, so this is the amount of time it takes to empty. The one thing you have to be careful about is looking at the scale of each axis. Oh, I got to take this. I'm sorry. Hold on a sec. So we're talking about, at this point, the tank is empty. Oh yeah, I was talking about scale, right? So you just got to be careful about counting the scale because oftentimes the scale is different. Sometimes it's not. So here, like 4 little squares is worth 20. So each little tiny square is worth 5, right? Okay, so over here, this is 105, 110. Okay, so how long does it take the tank to empty? 110 minutes. Okay, what characteristic of the graph can be used to determine the initial amount of water in the tank? What characteristic of the graph can we use to determine the initial amount of water? Yeah?
The
Correct, the y-intercept. Because initial indicates that time is 0, right? If time is 0, we are on the y-intercept. So this is the, I'm going to call it the vertical intercept. Right? And that's since time is 0. Okay? All right. Rates. At what rate does the tank empty? At what rate does the tank empty? So if you remember back in grade 10, this is like the rate of change. So you're looking at the slope of a graph. How do you determine the slope of a graph from the slope of a line, rather, from a graph? How can we figure out the slope? Yeah.
Don't you just pick like two places that are like the actual value, you're not guessing at the value?
Yes.
And then from there you can...
Yeah, so you need to look at 2 points, and you're basically looking at the change in y over the change in x, change in vertical over change in horizontal. So if you have a graph in front of you, I recommend just using rise over run, right? Oftentimes, if you have the intercepts, you can just use those points. So this over here is, this is 5, 10, 15, 20. That's about 22 gallons. And then we're going 110 minutes. So the rise here, to get from one point to the next, I'm actually going down. And then I'm going right. Okay? So if I'm going down, what's the numerical value of my rise? Negative, yeah. So negative 22 gallons, and then I go right 110 minutes. Okay, so slope is, or rate of change, is rise over run. And that is negative 22 gallons per 110 minutes. And when you divide that, I believe it's negative 0.2 gallons per minute. Okay? The negative sign indicates that the tank is emptying rather than filling. Okay? And then finally, state the domain and range within the context of the question. So let's look back at the graph again. Domain. So we want to think, okay, what's the minimum time value for this situation? What's the maximum time value for this situation? 110 minutes is the minimum, or the maximum rather. What's the minimum? 0. So time can go anywhere from 0 to 110. Okay, and what about the volume? What's the minimum volume? What's the maximum volume? 0 to 22, and that is the domain and range. Okay, so the domain is minimum is 0, maximum is 110. We're looking at time, and the range, minimum is 0, maximum is 22. The variable here is volume. And there we go. Okay, questions with that? All right, so for homework today, I would like you guys to practice these 5 questions, I believe. Yeah, there's 5 on the next 2 pages. For some of them, you're going to do these graphically using technology. If you don't want to use technology, you don't have to. We did look at that yesterday, so hopefully you're okay with that. If you need a refresher, though, I'll be around to help you out with that. And you can use the rest of the class to work on that.